Okay, so because the dynamics of gravity relates to constraint, the Hamiltonian just a linear combination of constraints. So when we talk about quantum dynamics, when we quantize this dynamics, we have to quantize those constraints. Yeah, that's the procedure we are going to do. Okay, so now let's come to the quantization of constraints. Quantization of constraints. And the scheme we are going to use is that firstly we have those classical constraints like Gauss constraint, Hamiltonian constraint, Muxin constraint. Those classical constraints. We call it CI. CI equals to 0. These are classical constraints. And then we are going to promote these constraints as operator. Okay. We are going to quantize this constraint and to write this constraint as an operator on our Hilbert space. And then we are going to impose the quantum constraint. Hat psi equals to 0. We are going to, well, in principle, the procedure is that we are going to solve those quantum constraints and obtain the solution space psi. So, constraints and solution space of psi is usually called a physical Hilbert space. Okay. Well, let's say schematically. Okay. So in the end, it is not exactly, well, this is just a scheme. So in the end, it's not exactly what we are doing because this procedure, in the end, it's turned out to be very difficult. But it's good to firstly set up this scheme and to discuss what is going on. Okay, so now let's come to the quantization of the constraint. All right. So let's first talk about quantum Gauss constraint. Quantizing Gauss constraint. So again, like what we did for area operator and volume operator. So we are going to first. So when we do the quantization, we first discretize the classical expression. So usually classical expression is defined on a continuum. But firstly, we need to discretize this classical expression to adapt on the lattice. And then we, once we discretize, we relate the classical expression to the lattice variables, and then we replace lattice variable to operators. And then we, that's what we mean by quantizing operators, quantizing classical expression to get operators. Therefore, again, so we do the same thing for this for the Gauss constraint. Okay, classically, well, Gauss constraint, classically, this Gauss constraint equals to just dA, right? And dA is a covariant derivative associated with to the Ashtar connection. Okay, so this is the Gauss constraint. Okay, and now we first need to discretize Gauss constraint. Discrete Gauss constraint. Discrete Gauss constraint. So now let me just give you the result. And this is your homework to verify the continuum limit of this expression indeed gives you the continuum Gauss constraint. I at the vertex. So here the Gauss constraint, this is defined at x, at every point x. Okay. So now when you discretize the expression, you get the Gauss constraint at every vertices. So this is defined to be at a given vertex. This defines to be sum over. So here you are going to sum over all the 6 edges around the vertex. So in our notation, so here is s equals to +1, and then I from 1 to 3, and it's just a sum of all the fluxes. V, I, S. Remember our notation of all the edges. So here we again set all the edges to be outgoing, and each edge is labeled as E, V, I, S. So I from 1 to 3, S is correspond to plus direction or minus direction. So here the Gauss constraint is just the sum over all the fluxes. Okay. Now this is your homework to verify that in you consider the continuum limit. Verify Gi in the continuum limit equals to mu to the 3 1 over, there's a prefactor beta 2 over beta dA dAi b plus order higher order mu 2 power 4. Okay? So this is just it's a simple verification if you use Mathematica. Okay? So again, so the hint is that it's something similar similar hint as you did for the volume operator. So you just use the formula that well, because it involves a forward direction, flux in forward direction, and also flux in backward direction. You have for the flux in the backward direction, you have to use this formula. I minus equals to 1/2 raised 100 I plus V minus I hat I plus and inverse I plus okay, and then here's H. Okay, so you use this formula to flip some edges, to flip some flux either backward to let me see. Okay, seems still recording. Okay. Okay. So this is the formula for P if you reverse the direction of edge, and you have to use that in order to verify this relation. And again, you also need to use of course the continuum limit of the flux. And then once you use this formula, you will get the covariant derivative of E. And so here you see this covariant derivative is because you have P sandwiched by 2 H's. So that's how you get covariant derivative. All right. So this is the discretized Gauss constraint, and these Gauss constraint equals to 0. This is also sometimes called closure condition. This is usually called closure condition, and this closure condition has a geometrical interpretation. The reason why we call it closure condition because it has interesting geometrical interpretation. Okay, so let me tell you the geometrical interpretation of this discrete Gauss constraint. Okay. In one sentence, so here the geometrical interpretation is actually making analog with, well, it's making interpretation of the Gauss constraint in terms of a geometrical cube. Geometrical cube of Euclidean geometry. Okay, so now let's temporarily just forget about everything from gravity. So let's just come to Euclidean geometry and consider just the geometrical cube. Okay, so this is just the Euclidean geometry, and you consider a cube. Geometrical. Well, cube has the geometry, and however, you can describe the geometry by using phase vectors. So consider the phase vectors. You just call this phase vector alpha, and you have in total how many phases? 6 phases. So alpha equals 1 to 6. Okay, so you consider a cube. You can view this cube is actually dual to this vertex, and for each edge it corresponds to a phase. Yeah, and then this vertex is dual to this cube. Okay, but let's consider this cube has a geometry, and this vector is three-dimensional vector P alpha. This is